Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right. Thank you all for coming this morning. It's my pleasure today to introduce you to Andy Ko, who is wrapping up his PhD at Carnegie Mellon University. He even tells me that the dissertation is written, so I'm totally impressed with that. He's going to be telling us today about a new way of thinking about debugging rather than the old breakpoint debugger.
Thanks for the introduction, Rob. So what I'd like to talk about today specifically is this notion of something I call program understanding, and it's been called lots of different names: program comprehension, software understanding. But basically, it's this activity that spans all kinds of software development work that we do, including fixing bugs, adding features to code, maintaining legacy code, understanding how components work together. If we want to do any of these activities in software development, we have to understand how a program executes and how that emerges from this code that we write into a program. Now, because it's such a fundamental part of software development activity, it's not surprising that it's time-consuming and that it's costly. In fact, the National Institute of Standards and Technology found a few years ago that it's half of the costs of actually developing successful software, and it's 30 to 90% of the labor that gets expended in building successful software. The interesting thing about this statistic is that it completely ignores all of the failed software, the software that never gets shipped. And that probably doesn't get shipped for a lot of these same reasons, that testing and debugging are difficult. The question is, why does it take so long? Why is it so costly? If this is such a massive part of software development work, how come we don't understand what makes it difficult? Now, one way to look at this question is, why does it take so long? And the second part of this is, what kind of tools could actually make it easier? And these are the two main focuses of my dissertation work, is trying to understand why it's time-consuming and difficult, and then designing technologies and interventions that actually make it easier and less time-consuming. And I take a very particular kind of approach to this research. It's a very HCI kind of approach. And I start off by trying to understand the tools that people use and how they actually do their work, what makes their work difficult, given the tools that they have access to. And then I design new technologies around whatever I understand about that activity from the studies that I do. And then I take those tools and I try to give them to people and see how it changes the work that they do. Now, this is all of the kinds of projects that I've done in my thesis work, in my PhD, and I want to talk about a subset of them today, particularly about the ones involving debugging. So this is basically what I'm going to talk about. I'll first mention some of these studies that I've been talking about regarding debugging and program understanding, and try to give a sense of what the actual problem is with software understanding. And then I'll talk about a tool that I've designed called the whyline and a few different instantiations of it. Then I'll go into a bit about its implementation and how it actually works, how it supports questions, which is what I'll talk about for the design of it. And then I'll go into an evaluation of it, both from a performance perspective and from a user's perspective. Does it actually help them in their activity to make them more productive? And then I'll conclude. So what I want to start with is that original question that I posed. Why is program understanding so difficult? Why is it so time-consuming? We already know a bit about this, and actually people have tried to look into this question for a long time from lots of different perspectives. So there are all of these different disciplines and fields and research areas across lots of disciplines that have looked at this question: psychology of programming, computer science education, empirical software engineering. All of these different areas of research have looked at this question of why it's difficult, but taken a very disciplinary kind of perspective on that approach. And so what I wanted to do in my studies was take it from the developer's perspective. What is difficult about the task as a developer works on this problem? So that was the focus of some of the studies that I want to talk about next. The first study that I did involved some novice programmers. There were 6 participants, and they were using the Alice programming environment. This is something that's been done at Carnegie Mellon by Randy Pausch and his students. And basically, it's a 3D programming environment where you can have objects in a world that have properties, and they move around, and you can animate them. So people build interactive 3D worlds with these things. I asked them to create a simple Pac-Man game using Alice, and asked them to think aloud while they were working, and had them work for about 2 hours. And their programming experience varied all the way from rank novice to very, very experienced, sort of 10 years of software development experience. And then I videotaped them while they were working so that I could go back and analyze what they were doing in their work. One of my goals was to find out, where do bugs come from, and when people see them manifested in their program's output, why are they hard to find? one of the things that I noticed first when I looked back on those videos was that all of these debugging sessions, when somebody noticed a failure, started with a why question as they were thinking aloud. So they would see Pac-Man do something they didn't expect and say, why did Pac-Man do that? Why didn't Pac-Man do this? And about 2/3 of those questions were negatively phrased. Why didn't something happen? So they would write some code where they expected some behavior to be produced, but it wouldn't happen for some reason. Now, the interesting thing about these questions was that as soon as they posed them, they would almost immediately come up with some hypothetical answer about why. They would speculate about what code was causing the failure that they saw. So why didn't Pac-Man do this? Maybe it was this line of code that I just wrote. Maybe it was this other function that's misbehaving. The problem with the speculation was that people were almost always wrong when they made these guesses. In this study, they were always wrong. 100% of those initial hypotheses that they formed were incorrect. And as a result of these incorrect hypotheses, there were a couple of negative side effects. Half the time that they worked on this task was spent debugging, and it was because they had to go through this process of speculating and then finding out that they were wrong and refining their hypotheses to converge on the right answer. And half of the errors that they actually inserted into their code during this 2 hours were a result of these debugging processes. So one person called this rebugging, adding bugs while you're debugging. So this was just a really negative kind of process where people would speculate about the cause of something as part of debugging it, insert more errors, and never really come up with a very accurate understanding of what their program was doing at runtime. So you might think, well, these were novices mostly. This was sort of a toy programming environment. This is something that's just dysfunctional about the way novices do things. So the next thing that I wanted to look at was what would happen if we had expert developers, people with some sort of experience, working on more complicated problems. So in the next study, I had 31 Java programmers working in Eclipse on a painting program. So this is the painting program they were working on here. And they could draw colored strokes onto a canvas, and the color of those strokes were controlled by the sliders on the left panel. And their job was basically to work on a few different bugs in this application and add a few different features into the application. They had about 2 years of Java experience or more, much more than in the previous study. And most of them had, I believe, a median of about 5 years of Java programming experience. And they used Eclipse 2.0 to work on these tasks. And I screen captured all of their work while they were working, much like the videotaping, so that I could go back and see what they were doing on a minute-by-minute basis. And what I found was a lot of the same things in the Alice study. When people saw their program fail, they would speculate about its causes, and they would reason about this in the level of output. So why didn't something in the output happen? Why did something in the output happen? Not at the level of code. And in this particular study, about 90% of those initial hypotheses about the causes of the program's output were wrong. So it was a very, very, very similar kind of trend with the novice study. And as a result, about half of the time that they worked was spent investigating code that wasn't technically relevant to whatever failure they were looking into. So there were no technical dependencies on the actual code for where they were looking in their source code based on their guesses about what was going wrong. The interesting thing in this study that I noticed, because these problems were more complex and I had many tasks that they were working on at once, was that many of their hypotheses about how their program was working and executing went untested. So they would work and investigate on a problem for a while, decide that it was the wrong path to go down and investigate something else. But as a result, they would have these inaccurate models of their program's executions in their head. And those inaccurate models would later influence other hypotheses that they would form about other debugging problems. So as a result, they ended up with a very jumbled and complex and inaccurate idea about how their program was executing by the end of the task. So again, a very dysfunctional kind of process. Another limitation, of course, is that this was in the lab, and these people didn't have that much programming experience. So again, maybe this was just a problem of context here. What do actual software developers do in industry? And how does their work differ? So the next thing that I did was come here. I was here 2 summers ago in 2006, and what I wanted to do was go into Microsoft software development teams and understand what kinds of problems do they have on a minute-by-minute basis in their work? What kinds of information do they look for? And I ended up looking at 18 different teams and observed their work for about 25 hours over the course of the summer. And the goal was really to watch on a minute-by-minute basis what kinds of information were they looking for. So things like, is my build done? What is my teammate working on? What was just checked in my source code repository? And what I ended up with was about 350 pages of handwritten notes with the help of Rob. And I converted those into about 4,000 information-seeking events. So at the unit of, is my build done? Those sorts of information-seeking instances. Now, there are a lot of interesting results here, and a lot of them potentially generalize outside of Microsoft as well, because as I found, Microsoft is not a monoculture. There are lots of different kinds of processes that the different teams used. What I want to focus on for this talk are some of the most common unsatisfied information needs, things that people looked for frequently but rarely found. And if we look at these, two of them had to do with this program understanding problem. The first one, and the most uncommonly found, was what code caused this program state? This is the classic notion of program understanding. Why did this variable get its value? Why are we here in the source code? How did we get here? 2/3 of the time, people didn't find the answer to this question. They would spend up to 20 minutes looking for it before they moved on to some other task. Another interesting one that's related to this is what code could have caused this problem. The difference here is this is a hypothesis formation phase. So a lot of the very experienced developers, before they would go investigate the causes of something, would go talk to their coworkers and find out, what do you think is happening in this situation? What do you think is causing this failure? And gather lots of potential explanations about things. And then the really clever ones would explore all of those possibilities in parallel. So it was a much more regimented and systematic way of exploring that space of possibilities of what their program was doing. Both of these were very collaborative. None of these kinds of problems were solved in isolation. They were done with the help of other people because other people had the knowledge that they needed to work on these tasks. And once they would form these hypotheses, then they would go off and investigate them. But again, because the software was so complex that they were trying to understand, they rarely ended up finding the answer. Now, when we combine all of these perspectives, there's a little narrative that starts to emerge about why program understanding is difficult. And one of the parts of this is that it's a very hypothesis-driven activity. People ask these why questions about things they see, about the pixels on the screen, and they wonder, well, what could possibly be causing this problem in the terms of the code in the software application? So there's a leap that they have to make. The problem is that most of those hypotheses are wrong, and as a result, people insert new bugs, they investigate irrelevant code, and spend a lot of time converging on a more accurate explanation of what their program did to cause a failure. And the most important thing here is that across these 3 studies and several other studies that I've done, this held true across lots of different developer populations. This isn't something that's really endemic to a specific population of people. This is sort of fundamental to the way that software development works when we're talking about debugging and failures. So to try to distill this narrative into just a simple observation about the problem with today's debugging tools, basically, today's tools require people to guess. You see some failure, you have to guess what happened, and then you have to go investigate if you're right or if you're wrong. And again, the problem with that is that in that leap, people guess, and they're almost always wrong that first time. So there's this big upfront process of coming up with an accurate explanation of what happened. So the observation is, the idea is for tools, is what if people could just work backwards from the pixels on the screen that they actually see, the things that actually went wrong in the program's output. If they could work backwards from there and just specify, this is what I think is wrong, the system can go back and automatically find out what was responsible for causing that output or preventing the output that they expected, and do that much more systematically than a developer can do. The other nice thing about this is that most developers are in charge of deciding what's wrong or right about their output. So that query that they form about the output is going to be much more on target than any guess that they're going to make about what code caused the problem. Yes?
So in the history of program debugging, Tony Hoare has promulgated the idea of assertions and done studies inside Microsoft. There are lots of product groups that use assertions, and fundamentally the idea there is that instead of waiting to see the output to see that your program is wrong, you have an intermediate assertion, and that assertion fires. It helps you localize where the bug is, because all the assertions before that point didn't fire, which were essentially indications that the state was correct, and so in these examples that you look at, has there been a use of assertions? Is there a methodology in place? Because this is a very common way to help address this issue.
Yes, assertions are fundamental to catching these kinds of problems earlier on. And I think this is purely complementary. I mean, if you have assertions and it can catch the problem that you're experiencing, it's going to be a lot easier to debug than if you don't have them. When you don't have those assertions or they don't fire and it's something that's not caught by the things that you've tried to anticipate, this is the problem that my work is focusing on.
So, but to be clear, in the code that you studied and you created, was there an assertion-based methodology used?
In the Microsoft study, yes. In some of the other studies that I didn't mention here in the talk, yes. Not in the two earlier ones for the Java programs using Eclipse or Alice. Okay? So this brings us to the idea of the whyline, which is what I want to talk about for most of the rest of the talk. And basically, the idea is to work backwards from output, from what you see in your program's failure. And I've created 3 different prototypes of whyline-like tools. And I'm going to talk about one of them in detail, but first I want to mention 2 of the others, just to give you a sense of the breadth of the idea and how well it applies in different contexts. And then after that, I'll talk about its implementation and some of the evaluations that I've done of the tool. So the first one that I did was a whyline for Alice, which I mentioned briefly before. Don't worry too much about the questions or the answers here. What I want you to see is that there are basically 2 things that I added into this environment. There's a menu of questions that are automatically generated from the source code and from an execution history. And the developer can choose one of those questions and then get an answer that's shown in the bottom that's presented as a timeline of basically causality. This happened because these things happened and so on. That's the basic interaction. In this particular context, for novices using this to develop these 3D interactive worlds, and in one study it reduced debugging time by a factor of 8 and increased people's productivity by about 40%. They finished 40% more tasks than people using regular tools. So this was very, very helpful and very successful for this particular population. The next example of a kind of tool that I did was sort of outside the scope of software development, but very similar in its approach. And so what this was a whyline basically for applications, for people that aren't writing code. So imagine you're using Microsoft Word and you're typing along, and all of a sudden it capitalizes your word at the beginning of a sentence, but you didn't expect it to happen for some reason. This is a way of pointing to that word and saying, why was this auto-capitalized, and getting an answer about why it was capitalized. The key difference here between the software development situations and applications is that the answers aren't presented in terms of code because the user can't change the code, and they wouldn't want to anyway. Instead, they're presented in terms of all of that input, that user modifiable state, the application state, everything that affected that particular feature working in the way that it did. So again, in this situation, it was still very quite helpful. They completed the same tasks 20% faster than people using regular help features, and 30% more tasks with this approach as well. So that's an example of novice programming, an example of application use, not programming at all. Yes? In the first study, there were, I believe, 8. And in this particular study, there were 20.
So it's between, like, different people, 10 each in each
Yes,
condition.
in each condition.
Yeah.
And in this particular, I mean, all of this has to do with just how many you need for the effect to show up. And I think what this says, because my sampler sizes were so small, was that it was such a profound effect that we could find it even with very small populations. The question from these 2 prototypes is, how does this generalize to this larger scale? How does it work for big programs that have massive complexity? And can I really derive questions and give answers about that kind of complexity? And now I can confidently say that I can within the scope of Java programs. And now I have a Java prototype that supports graphical and textual output that works for some of the biggest open source applications that I've tried it on. So I'd like to basically give a demonstration of how it works in detail, and then talk about its implementation. So to give this demo, I want to take a look at a simple bug from one of my prior studies. This is basically that painting application that I mentioned earlier. And there's a canvas on the right where the users can draw strokes, and 3 sliders for red, green, and blue that controls the color of those strokes. Now here are the failures. The first stroke they draw is good. It should be green because the green slider is all the way up. But when the blue slider is all the way up and the other 2 are down to 0, the preview panel of what color will be drawn is black, but it should be blue, right? And the stroke that they draw on the canvas is also black, but it should also be blue. So what we see here are basically two symptoms of this failure. There's probably one thing going on here that's causing this problem, but it's manifesting itself in multiple places in this program. So some obvious questions that people ask when they see these are, why didn't that color panel change? And why is that stroke black? Or why isn't it blue? These are natural things that a tool should be able to allow people to ask questions about to get them closer to the causes of these failures. Before I show you how to use the whyline to do these things, I'd like to show you the baseline. What do people have to do today with regular tools to address these kinds of failures?
Can you say quickly, is that a real bug or was that seeded?
This was an application that I wrote myself for this Eclipse study that I mentioned earlier, and all of the bugs that were in the application were there as a result of me writing that code, unintentional. And then I went back and found bugs through testing and then used those for the real task. So they were real, but it was just me. So this is what people did in this application. And I should mention, it's not that complex an application. It's about 500-600 lines of Java code, still across about 9 or 10 source files. And so there's some work to understand how they're all related. This is what it looked like over the course of about 10 minutes. I'm going to speed this up at 30 speed so we can get through it. They asked this question, why is the stroke black? And then in the process, first started off by saying, well, maybe this slider isn't initialized properly, and explored some of the source files to find the initialization. And they said, well, maybe it's not connected to things properly, and started exploring dependencies in the source code. Thought maybe it was an argument problem, and explored the documentation on the constructor. Thought maybe the color wasn't computed properly. And only in the process of exploring all of those files did they accidentally stumble upon the actual bug. It was apparent from the source code what the problem was. And this happened over and over again across these 31 participants in this study. It was basically, this is how debugging works. Lots of exploration, lots of navigation of dependencies, a lot of guesses about what's going on that drove the investigation into the source code. Now, I won't tell you what the answer is yet, what the bug is. I'd like to show you that with the whyline. And so basically, I'm going to go take two different takes on what kinds of questions the whyline supports. The first one is, why was that line black? Yes?
Actually, before you go on, I had a simple question about the previous slide, which is, I mean, simplistically speaking, wouldn't it be the case that if you put a breakpoint in the right place, you'd be able to observe quite a bit about what happens to this particular execution pass as far as changing the slider?
Yeah, I should have mentioned before, the fundamental problem with breakpoints, print statements, almost any tool that requires you to reason at the level of code is that you have to guess where to put that breakpoint, or what to print out, or what to form a query on, or what to assert. And if you,
in this case, the guess is not really that complicated.
People made guesses over and over again on this task, and 89% of the time were wrong, even with all their experience debugging.
The event handler on the slider is not really the right place.
You'll find out. But people guessed that in many cases, but spent a lot of time, up to 5 or 10 minutes, trying to find out where that event handler was. So let's look at what the actual problem was using the whyline. Let's start with, why was that line black? Basically, the way the interaction works with the whyline tool is that it's going to record an execution history. So the developer will record some demonstration of the failure of whatever bug that they were working on. And then they'll load that execution history, and the system will generate a whole bunch of indexes and make it fast to support questions and answers. And then the user asks a question. And this basically works by pointing to what you see and clicking and exploring a menu of possible questions that you can ask. And what we see here are basically a primitive level question about some primitive level argument of some output on the screen. So they chose this particular line segment and are asking, why is that line segment black? This is a question about one of the arguments that's passed into the renderer for painting lines into the Java rendering API. And I'll mention later some of the higher level questions that, about things that this low level output represent. Now, when they ask this question, why did the color black equal black, what the system's going to do is go find the cause of that color black being used, and then the user can go back and trace to find its source. Yes?
So there's some method that draws a line segment, and that has arguments x1, y1, x2, y2,
Yes.
and so on, and that's the source of the vocabulary of the questions you're prompting.
Yes, specifically for this low-level question, these questions about low-level primitive output. And there are many other types of questions that are derived from those.
This is a question about a library call not really a question about the internal state of the buggy application.
No, just a library call. And in this case, the color wasn't a direct parameter on this call, but some data dependency on a graphics context where a color was set and then a line was drawn. And I should mention here that the only assumptions I make about these applications are that they use that particular rendering API. I don't assume a particular user interface toolkit or anything else about the application, just that low-level rendering API. So let's see what an answer looks like for this simple primitive question. When they ask this, it's basically going to show two things, source code on the top and an answer on the bottom. And if we look at the source code, what it's pointing to is this reference to this field called color, and it's highlighted in orange there. It's a field reference in Java, and the same corresponding event is shown down on the timeline here. This is representing that execution of that particular field reference. Now, there are a couple different things in the interface, and that the basic interaction is that once you ask a question, you ask follow-up questions about other dependencies on things that are in the answer. So an example of that is down here, this particular field reference has a few different other questions about it. Why was this code executed? How was it reached? This is sort of a control dependency question. So what called this method? What conditional was evaluated that led this to be true? But also a couple of different data dependencies, these blue arrows. So a field reference in Java has two data dependencies, the object that we're talking about and the particular value of the field. What we wanted to know was why was that color black? Why was that field color black? And asking that question would take us back to the source of that color. And then just a few UI notes. The same questions appear up in the source code. Developers vary on whether or not they're thinking about things in terms of source code or time and execution history, and I found that having it in both places and mirrored was important because people would be thinking in different terms at different points in their investigation. And then another thing from the user interface perspective is that when you hover over one of these questions, the UI will show you where you'll jump to if you ask that question. So we can see here that by pointing over why was the color black, we see the color was black because it was instantiated down here. So when we choose that question, it'll jump to that place in the source code. So that's what the user is going to do next, is they're going to choose that question. I believe they're going to point to the one in the upper right and say, why did that color for that field equal black? And they click it, it's going to jump to this source code right here. And if we look at this source code, there's sort of an obvious copy and paste kind of problem. There's a reference to red slider, and then green slider again. So the problem is here that it should have been blue slider on that last argument, but it wasn't. So it's a pretty straightforward kind of bug. When people used regular tools, even if they guessed that it was some sort of event handler problem, they spent 5 to 10 minutes finding that event handler and really knowing that it was the problem. Even when they saw the source code, then it was apparent. Here, an experienced user using the whyline could have found this in 30 seconds to a minute, and did when I gave it to people to actually try to use. Question?
Can you see what the values that it got from the slider are for all three of those?
Yes, actually they're right here in the question. So why did get value return 0? So it returns 0 in each of those cases. And then some other things I haven't shown in the user interface. You can show your standard call stack and local variable values and so on to see all of these other kinds of details too. And if you hover over the names in the source file as well, you can see their current value based on the current time that you're at in the timeline. So this was the bug, relatively. Yes, Andy?
So I have a question about the system itself. So in terms of being able to click on something on screen, are you recording every single pixel that's on that screen so you could point back to the line of code or the primitive operation that actually drew that pixel?
I'm recording at the level of if you think in terms of vector graphics, at the level of lines and circles and rectangles and text. So not at pixels, but yes, at that layer of rendering. So I'm recording everything that happens at that layer of rendering and everything before it.
Then what pixels that affect?
Yes.
So you can map it back.
Right. So it's mapping everything that's shown on the screen back to everything that happened inside of the application. And I'll talk about that in more detail when I talk about the implementation. One last example. Another way to phrase this question, and this is another approach that people took to this problem, was why didn't that preview panel change? They may not have even noticed that the stroke was the wrong color, but just that panel stayed black as they moved the blue slider. So a lot of people phrase this question, why didn't that preview panel change? So let's look at how to ask this question using the whyline. Here, what we want to do is find out when that slider was being moved. And so the user is going to use the slider down here, this time slider, and find when that slider on the top was being moved. And then click on that black panel and say, why didn't it change? Let me talk about how they find that question in the menu. Basically, what happens when you click on any low-level primitive output, the system is doing lots of analyses to find other concepts in the application's implementation that are related to that low-level output. So one thing that was responsible for drawing that black rectangle was this J component called current color component. And basically, that's extracted from the source code. And so they can see, OK, there's this thing inside of the application that was responsible for drawing this black rectangle. And then, once they find that, the thing can go into ask questions about that component. And one of those questions is, why didn't paint component execute? That's the method that drew that black rectangle. So all of the questions that appear here are basically anything having to do with output, anything indirectly affecting things drawn onto the screen. It excludes questions about other things that don't affect the graphical output in the application. Now, when they ask this question, the query is basically, why didn't this particular method execute at this particular time in the program's execution history? And I'll talk about how it does that analysis a little bit later in the talk. But basically, let me show you the answer now. What it says in this case, in response to this question, is actually paint component, this method that we thought didn't execute, it did execute. So it allowed us to ask a question about something that we thought didn't happen, even though it did happen. And that's actually really important, because a lot of the kinds of problems that people have are these misperception issues. It looks like that black rectangle wasn't being repainted, but actually something was being painted over and over again with the same color. So misperception is a serious kind of problem, and this allows the tool to get people to express these misperceptions so that it can correct them.
Are you providing a misdirection and reinforcing that false impression that paint component didn't execute?
By asking that question, they're making an implicit assumption that something didn't re-execute, right? And so, but in that sense, I am reinforcing it. What I found, though, through a lot of experimentation and iteration in the design is that if I don't support that question, or I say the answer up front, people will often just overlook the question, because they'll believe so strongly in what they see that they'll just ignore the possibility that it actually did execute and go find some other question that lets them ask what they actually want. So there's a little bit of interplay here between what people's perceptions are about what actually happened and how strongly they believe it, that I have to modulate with UI design. So what people do when they see this answer is they say, oh, okay, well, of course it executed. It just probably executed with the same color every time, and so it repainted the same way. So what they would look into next is, well, okay, what color did it paint with, and where did that color come from, since it was black every single time? So what they do in this situation is, like a regular kind of breakpoint debugger, they would step forward in the method and find out where that color came from. So they use this button next in method. It's basically like a step command in a breakpoint debugger. And they step through the different statements in this method. And then, unlike a breakpoint debugger, when they find a statement that uses that color, they can trace back and find the source of that color, about where that color was computed. So again, we'll ask the same kind of question here. Why did the color equal black? And when they ask it, it'll jump back to the same place where that color was computed for the other question that we looked at, in this case right here, where the exact same bug that they were looking for appeared in the other example. So as you can see, each of these different kinds of questions takes more or less work depending on how far that question is from the actual cause of the problem. But regardless of what question you start with, as long as it's some symptom of the same failure, they'll all basically lead to the same place. So hopefully it doesn't seem too much like magic, but if it does, yes?
But that doesn't cover the case in which you really didn't call it. So what do you do next?
You really didn't call it, and I can talk about the algorithm that I used to analyze that situation a little bit later. What they would find is that there was some reason why it wasn't called, some other methods that weren't called that needed to be called for that to happen, and they would have traced back and found those. And I'll mention a bit more about this later. So let me talk about the high-level view of implementation. Developers edit, compile, debug right now, and the whyline is asking them to replace this debug process with basically first record the demonstration of your failure, load that recording, and then in a post-mortem way analyze that recording by working backwards from output. And what the system is doing for those three different steps is instrumenting some bytecode and instrumenting the code to capture that recording, and then converting all of that history into this random access format, and then extracting questions from that code and answering questions about it once they've loaded up that recording. So I'm going to talk about these three in a little bit more detail. In the recording process, Java dynamically loads class files as necessary. So every time one is loaded, the whyline intercepts that class file, does a bunch of data flow and control flow analyses on each of the methods in that class file, and inserts instrumentation into different parts of that method to capture that execution history as that method executes. All of those instrumented class files are then cached so that for later executions, the instrumentation process takes much less time because it only has to instrument those classes once. And then the history that it actually records is a serial thread history. So each of the histories for each thread in the Java program that executes are recorded independently. And then each of the events in each of those histories has a unique event identifier that allows us to know how those threads were interleaved over time. So we can get at questions about, why were these two methods interleaved when they shouldn't have been. In the loading step, basically it's dealing with static information and dynamic information. So it loads up all of the class files that were loaded over time. It also loads class files that weren't loaded, because if we have questions about something that didn't execute, we need to have access to all of those things that didn't execute as well. And builds a call graph, associates fields with declarations and so on to build up this knowledge about what the program is. And then for the dynamic information, it takes all of that serial history and converts it to random access dynamic kinds of history. So an example is, in many cases, the whyline needs to know what were all of the calls to this particular method and all of the different instances that were called on for this method. There's a table that's built in memory to know what all of those calls were so that the system can quickly get at these kinds of queries internally to answer questions and to derive questions, in fact. Mostly just indexing of lots of different types of dynamic information in memory. Then this is all sort of intelligently indexed and cached to disk and throttled in and back and forth into memory, since this is actually quite a bit of data. Before any users can ask questions about any of that history, we need to parse all of that history and come up with some sort of interface for people to be able to point to things. So the way that works is basically different for each of these different modalities. So the prototype that I have supports graphical output, console output as text, and exceptions that are thrown. You can see a picture on the right there. If you have a purely console-based application, you can still ask questions about anything that it prints out, values, errors, things like that. For the graphical case, it's actually quite complex for Java because you have buffering in a lot of situations. An example is when you're drawing a button with a gradient. Gradients are expensive to paint, so it buffers painting of one little section of a gradient and then uses that buffer over and over again all over the screen. So when you're pointing to something on the screen, there's not always a direct relationship between a call and the pixels on the screen. There's a lot of indirection in many cases. So I have a simulator that analyzes all of that and makes sure that when somebody points to something on the screen, I can find that call through all of that indirection to associate the pixels with something that executed in the source code. And then another important part for the graphical output is to analyze all the visual occlusion in that so that when you move a slider, that this can be interactive like a movie, basically, and find any particular point in time that you want to ask about without having to wait for the system to find out what was actually appearing on screen. So let me talk about the different types of questions that are supported. I mentioned these primitive questions about arguments that are passed to low-level output calls. So a call to fillRect, for example, has a position and some dimensions, and there's also some indirect dependencies on the color and the paint stroke that's used. These are basically the only assumptions that I make about an application with graphical output, is that they use these rendering interfaces. All of the other knowledge about questions is extracted from these low-level calls. An example of that are questions about field data, fields in objects that indirectly affect those arguments that are passed into that primitive level output. So if you imagine a combo box or a drop-down menu in a UI, there's going to be some list in memory somewhere or some set that's going to determine what items appear in that menu. So what the system does is follow all of those data dependencies in the source code to find out what other data and data structures indirectly affect those low-level primitive arguments. So at some point, that combo box was affected by the model, and it used that model's list and a particular item from that list to draw a label onto the screen. So the system tracks those data dependencies and then inserts questions about those data structures. Yes?
So are you doing runtime data flow analysis, or are you just doing static analysis to find all the places a field could have been set versus which ones actually affect that?
I'm doing both. The positively phrased questions, why did ones, are runtime analyses, along with static. You have to do both. And then the negatively phrased ones, why didn't something happen, those are purely static. So this is one kind of higher level question about data that affects output. Another kind is data that indirectly draws output. So from that painting application that we saw before, we were asking this question about an individual line segment. It turns out that in this program, all of those are aggregated into a list into something called a pencil paint. So in addition to being able to ask about that individual line segment, you can ask about the whole aggregation of them and ask about features and properties of that pencil paint. So in this application, for example, it had a thickness field, which was a global property of a whole stroke. So if you wanted to ask why the thickness was 5 or why didn't it change after a certain time, you could also ask questions about that. There are a few issues that span generation of questions that are important, and they all have to do with filtering, because as you might expect, there could be a lot of questions that we could generate from source code. How do we decide which ones to put in? How does the tool decide which ones to leave out? One way to do that is by a notion of familiarity. And the problem here is that in any complex kind of user interface toolkit, especially for graphical output, you have a lot of intermediaries, a lot of delegates, a lot of proxy classes. So you imagine a button class that a user might instantiate in their source code. There's actually often a look and feel delegate that decides how to draw that button. And somebody who instantiates that button may never know that such a delegate exists. And so if we look at the call stack of all the calls that were responsible for drawing a button, we wouldn't want to include questions about those delegates because the developer might not know about those classes and wouldn't know what to ask questions about them anyway. So I define familiarity basically as either some class that's declared in editable source. So if the user has access to that source and can recompile it, then it's something that is familiar. Or if they reference a class in some editable source, then it's familiar. So if they're instantiating a button, then a button is familiar. But they're not instantiating a button look and feel delegate, so that's not familiar. So I only include questions in these menus about classes that are deemed familiar by this definition.
I guess I'm surprised that you do filtering, which can induce real problems now, if the bug actually isn't something you filtered out.
Yes.
If it is a problem in that look and feel delegate, right? As opposed to, say, having a more button at the bottom where you shuffle all the uncommon cases, right?
Right.
Is that just a UI choice?
No, this really comes down to the fact that I'm really trying to get people to start from how they're conceiving of output. So if the problem really is in a look and feel delegate, they're probably going to phrase that question from that primitive level output, and then it'll work backwards through that look and feel delegate because it was the one doing the rendering. If they think it's a higher level problem and ask about the button, and it was a look and feel delegate problem, they'll probably have to ask a different question too. What I found so far in a lot of the studies is that people tend to phrase their questions sort of right above the level of where these problems happen, and then they have to work some distance backwards to get there. They rarely go too high a level of abstraction and then have to work their way back down. Obviously, that's up to debate, and it's something I only have a little bit of empirical evidence about. Yes?
I just have a question about the negative questions that you put into your user interface. I mean, in some sense, why did pencil paint not do X or not do Y? Why didn't it jump over the fence? I mean,
I'll get to that.
Like there's a lot of questions here that you can stick into your UI even without filtering or with filtering.
Yeah, and the basic concept behind this design is that people only ask questions really about what they expect the program to do. So if they're debugging Microsoft Word, they're not going to ask about why a slide didn't appear after I pressed X, right? So there's some implicit scoping that people naturally do in their expectations about what systems do. And I'll talk more about the different kinds of questions that you can't ask in just a bit. Another kind of filtering that I do is filtering by modality. So if you're asking questions about graphical output, you need to be able to filter out questions about textual output and all of the things that indirectly affect it. So I start from those low-level primitives and trace back all of those control and data dependencies and find other classes and data structures and fields that indirectly affect those types of modalities. And so I can also filter in that sense by dropping out all of the textual questions when you're looking at graphics. And this is another way of reducing the size of these question menus. Let's talk a bit about answering these questions. For the why did questions, these queries essentially refer to a particular execution event in this execution history, and then it computes a precise dynamic slice backwards from that event in the history. And if you don't know what slicing is, basically it uses two different concepts, one of control dependencies and another of data dependencies. I compute the control dependencies on demand. They're pretty quick to compute. And the data dependencies are essentially what we saw in the timeline visualization with those follow-up questions. So when somebody clicks on one of those blue arrows, they're incrementally building part of that slice. They're basically traveling back and looking at those data dependencies in time. And then to present them, the structure is basically those control events contain data events and other control events as well. So this particular user interface, I don't have time to talk about too much, but it makes it very flexible to navigate and grow that answer over time. And then one last thing about the why did question answers. When we asked about where that color came from, you might have noticed that it jumped immediately to this instantiation of the color. There was some magic going on there, and what that magic is basically an observation that a lot of problems when you're looking at data are the data dependency flows, not the control flows. And so if this color was wrong, but it was just passed as a value to lots of other, through lots of other methods, completely unmodified, we don't care so much about which methods it was passed to, but where it was constructed, where it was set, where it was modified. So by default, when somebody clicks on one of those data dependency arrows, it jumps to the expression that computed it, the constructor that computed it, rather than going through those intermediate steps. You can also follow those intermediate steps, but it tends to be empirically less common that those control dependencies are the problem. For the why didn't questions, yes?
Do you mean last assigned to, for example?
Yes, last assigned to some expression that recently assigned to something else. The why didn't questions refer to some unexecuted instruction, one or more of them potentially. If we wonder why a field didn't get reassigned, there may be many potential assignments in the source code to it. And then along with that, some particular time at which we expected that instruction to execute. And then for some cases, for some questions, it might also have some particular object in the heap that it's referring to. So if we're asking about a certain button on screen, we want to make sure that the question is analyzed from the perspective of that particular button and not other buttons. And this is important because if we're going to ask about some question about why something didn't happen from the source code and not from the output, how would you specify that button other than by pointing to it? Yes?
Questions are sort of timeline based in some sense. So let's say I had a loop that was supposed to go 100 times, but instead it only went 99. It's not I can't ask the question. Can I ask the question of why didn't this execute one more time? Or
no.
Can I somehow filter down to that last execution that's missing?
This goes back down to asking about output and not about code. And this particular enforcement is just on that first question. Every other question that you might ask after you ask a question about output can be about as much about code as you want, but it's all about starting from output because the observation from the studies was that that's the particularly costly, expensive choice that people make is where to start their search. Let me talk a bit more about the questions that I don't support. Actually, these are the different kinds of why didn't questions. I support questions about fields in objects, about methods that weren't called, and also about classes that weren't instantiated. I haven't mentioned an example of that, but imagine you just write some code to make a dialog appear in response to some event, and you test it and the dialog doesn't appear. You want to be able to ask, why didn't that window appear? Or why didn't something appear on screen? So if you click in the white space of anything in the graphical output, you can ask questions about those kinds of classes of output that you expected to be instantiated. To answer these why didn't questions, basically there's several different cases based on the definition of Java programs execution that you have to go through. So if you have some instruction in mind that you expected to execute, first you want to look at why didn't that method execute? And if it didn't execute, it may be that there are no calls to that method, so that's one potential answer. There were no known calls, it's not reachable. The other possibility is that there are many calls, and so the algorithm recursively steps back to all of those callers and starts building a chain of methods that weren't called, which the developer can then go back and find out where they expected something to actually be called. If the method was executed, there are lots of different reasons why the instruction inside of it wasn't reached. One is that maybe the method was called on the wrong instance. So if we were talking about this button, but there was a call on this button, then it's going to ignore those calls. In some cases, it's because you've referenced the wrong variable, and so you're calling on the wrong object. An exception might have been thrown, which jumped over the desired instruction. If that instruction was control dependent on some conditional in that method, then if that conditional executed, then it branched in the wrong direction. So if the instruction we wanted was here, and the conditional branched this way, then that conditional is the reason for skipping over it. And then if that conditional didn't execute, then again we recursively go back and trace back to build a chain of conditionals that didn't execute in the right direction. Finally, if in all other cases were false, then the instruction was about to be executed, but the thread or the program itself halted, so it didn't reach it yet. And then these answers for these why didn't questions are presented as follows. Basically, the answer is some unexecuted subgraph of all of these control dependencies. So each of the nodes in this answer are some unexecuted instruction or method, and each of the incoming edges are unexecuted branches and calls, or branches and calls that were executed but in the wrong direction or on the wrong object in memory. And so the developer can go back and trace through all of these things and find out where they expected something to be called, and usually somewhere in that chain is some place where the bug was. There are a few different types of questions that I don't support. One is questions about continuous values. So why wasn't x 6.2895? And there are a couple different reasons for this. One is that even if you can generate answers to these, they can be very expensive to compute, and the answers can be quite large. So they're not actually that helpful. The other problem is that people don't always know what the exact value of something should be. They might know that it's greater than 0 or less than 10, but they're not going to know a concrete value. So rather than supporting these questions, I just support why didn't some variable change after a certain time? Or just asking the positively phrased question, why does it have the value that it does? Another kind of question that I don't support are these forward reasoning questions about input. So why didn't that slider do anything whenever we moved it? And the problem is that something almost always happens when input occurs. It may not always have a visible effect on the feedback of a program. But there's no way to really filter all of those things that do happen. So by asking from the output and working backwards, there's some specification from the developer about what part of all of that execution they're interested in. Okay, let me conclude about the evaluation, and I'll quickly go through some of the performance characteristics about my prototype and then talk about a user study. One issue is slowdown. So when the instrumentation is happening, how much does it slow things down? Regular profilers for Java tend to have a factor of about 2 to 4, and the whyline for Java is more on the order of 4 to 8, depending on the application. And it depends a lot on user interfaces are fairly lightweight. They're not doing much. They're in idle state a lot. If you're instrumenting a compiler, on the other hand, it's doing something constantly, so the slowdown can be a lot heavier. You can still use user interfaces pretty easily to demonstrate failures. The size of the recordings that are generated are smaller than you'd expect, especially for user interfaces. So the largest one I have is this Java compiler, which is about 300 megabytes, and it compresses very well because part of these recordings are all of these concrete values of variables in memory, and there's a lot of patterns in that are picked up on by compression algorithms. So these are on the order of 10 to 20 megabytes for about a minute of interaction. These are things you can store on servers and have people collaborate on and annotate together. And then finally, for loading time, on first load, it needs to convert all of that serial information into random access information. And that can take some time, on the order of about a minute for some of these traces that you see here. Once that's done, on all subsequent loads, it loads pretty much instantaneously because it has all of that random access data already converted. So it works pretty well as an interactive tool after that first load, but that first load can be time-consuming. So let's talk about the comparison study. I basically had 10 people using the whyline and 10 people using conventional debugging tools, breakpoints, print statements, things like that. I also had a third condition where they used dynamic slicing tools. I didn't end up capturing all the data because people refused to use them. They said they were useless after they tried them, and I couldn't get them to actually complete the task. They would just use the breakpoint debuggers anyway. So that one I won't talk about. Both of the groups had access to modern IDE features, things like showing a declaration, showing callers, things like that you might find in a Visual Studio or Eclipse. And then a few notes about the conventional debugger. Rather than using a commercial one and running a live program, Instead, what I did was simulate a conventional debugger using a whyline trace. So what this meant was that they could set breakpoints and step through things as normal and even insert print statements that didn't have side effects. But they couldn't modify the program and re-execute it in different ways. And of course, this is an obvious limitation in the way that they actually do their work, because that's a strategy that a lot of developers have. It's not always a good one, of course. And so I think I influenced them in a good way rather than in a bad way, but we can debate about that. The application that I had people use was Argo UML. This is about 150,000 lines of source code, and there are almost 30 external libraries that it uses. It's an open source project for creating UML diagrams and generating source code from them. And I chose 2 bug reports from the application, basically one that looked easy from a surface perspective and one that looked difficult. And these were real bug reports that had already been fixed, and so that I could compare people's answers to the actual changes made in the open source project to see how well they aligned with design goals. The first one was titled Remove Report Usage Statistics since it does not do anything. That was this checkbox right here in the center. So their job was to find out where that was added and make sure that it was removed from the UI because it was a feature that wasn't finished. It wasn't as easy as it might seem because they couldn't search for the string in the source code because it was a localized application. So the string appeared in a compressed file on disk for lots of different versions of the application in different languages. So you couldn't just search for it. It was trickier than it looks. The second one was titled Problems with 2 classes with the same name in different packages. So there was a UML diagram with 2 classes of the same name in different packages. They were both supposed to appear in this menu of class names, but only one of those would appear. So if they were both named my class, you would only see one instance of it, and you wouldn't see which package it was in either. So they were supposed to diagnose why that list of items was constructed the way that it was. They were chosen from a particular version, and I chose them based on criteria about how much discussion and transparency there was about the solution that was eventually checked in by the application. But it was a fairly informal thing. I was basically looking for something that would take a short amount of time and something that would be much more challenging. And it ended up being the case, mostly. So I told participants, identify the cause of the problem. Rather than actually making the change, which isn't something most developers do, they were required to write a change recommendation about how they would change it and what they thought the actual problem was. And this was code they weren't familiar with, so this was a natural thing to do because whoever was familiar with it would be much better at knowing whether it was the right answer or not. And then they were given 30 minutes to work on each of these problems and told to emphasize speed over the confidence and the correctness. The problem here was that they could spend 30 minutes trying to decide if they were right about their answer, even after finding the answer in 2 minutes. So what I wanted them to do was come to some conclusion about what they thought the cause of the problem was, but not spend too much time on being really sure about it. And then I measured time on task and success. The people that were in the study were 20 master's students in software engineering, all non-native English speakers, coincidentally. And they had a range of 0 to 10 years of software industry experience with a median of about 1.5 years. And there were lots of other measures that I took that they didn't differ on. So it was a fairly homogeneous set of people. In terms of the results, for task 1, all of the whyline participants solved the problem, and they solved it in about 15 minutes, usually getting to the cause in a couple of minutes and then spending about 10 minutes seeing if they were right about their answer. The control group, only 3 of them solved the problem, and they all spent almost all of their time looking for the problem. And they used the same kind of strategies that you'd expect, navigating source files and so on. For task 2, it was much more difficult as I expected. 4 of the whyline participants solved the task and in about 30 minutes, and they spent a lot of time gaining confidence about their answer. None of the control group participants solved the problem, and in fact, in about 15 minutes, 4 of them said that I'll never find the answer to this. This is just a disaster. It's too complicated. None of the whyline participants gave up in the course of that study. A few observations about these 2 tasks and what it says about the tool. People still needed to choose their questions carefully. They needed to deliberate about exactly which question they wanted to ask. The important thing here about the whyline is that it made this choice of question explicit. And so I heard people thinking aloud and saying things like, what data do I really want to know about here? I didn't hear this deliberation in the control group participants. They sort of just implicitly chose where they wanted to go with the task and went forward. If you choose the right question, you get to your answer a lot faster, but if you choose a question that's sort of indirectly related to the failure, you'll still get there, but with more work. And that's similar to the demos that I was showing earlier. And finally, there's a notion here that the whyline's giving confidence about causality. A lot of the control group participants even found the methods and functions that were causing the problem, but had no idea that they were related to the output that they were trying to diagnose. So they would get to the right place through their navigations, but have no concept of its relationship to the problems they were trying to understand. So, yes?
Of the whyline, I don't know if you'll get to this, but how many of the whyline people explored the wrong questions in the whyline interface?
Deciding what a wrong question is difficult because oftentimes it's just further from the actual cause of something. I think that...
Think aloud versus what they picked.
Oh, well, let me chat about how well these questions map in a bit. Just some quotes from the study that were unprompted. It's so nice and straight and simple. My God, it's so simple and cool. When can I get this for C? People were really enthusiastic about the approach, and everybody wanted it for their favorite language. So that was a very positive kind of result, even beyond the data. So let me talk about some of the limitations here about how well it works and how well it doesn't work. Obviously, memory and performance are a significant issue. It's a very heavyweight kind of debugging. It's not as simple as inserting a print statement. So it requires a real commitment to actually use in your work. It's infeasible for long executions and things where timing matters, where you can't control a clock. So real-time applications, it doesn't work well for because there's probing going on. The quality of the questions that get extracted depend a lot on the quality of the identifiers in the source code. So if all of your classes and variables are named X, Y, and Z, all of your questions will be why didn't X do Y and Z? And so that doesn't make much sense unless the identifiers make sense. And similarly, the quality of the questions and the answers in terms of their precision depend a lot on the type information available in your program and in your language. So dynamically typed languages are much trickier for the whyline to support because it's much more difficult to establish a relationship between some primitive level output and all of the other source code in the application. The whyline is not generating change suggestions. It's just talking about causality. And another way to state this is that it's really good at finding where your buggy algorithm is, but it's not good at telling you why your algorithm is buggy. So if you eventually find out where the wrong value is being computed, but it's being computed by some very complex machine learning algorithm, if there aren't any specifications about what that algorithm is supposed to be doing, it's not going to be able to tell you what's going wrong. So it's really focusing on this particular kind of problem of locality in source code. And another point is that it's very good for functional kinds of correctness, but it's not focusing on other types of software qualities like performance and usability and robustness and other qualities like this. It's really focusing on deciding what's right and wrong. Yes?
So two questions. One is that it seems like this might have some trouble scaling to things that are very distant from the UI, since you're very focused on asking questions about the UI. If you had any thoughts about how this might work, if at all, for components like that?
I have a lot of experience testing it with UIs, and I found that a lot of the kinds of traces that people have to go through for UI problems are very shallow because those event handling traces are shallow, right? There's a very short distance between the input and the output, the corresponding output. So that doesn't seem like too much of a problem. The bigger problems are for very heavily data flow driven applications. So in compilers, for example, if you have some error message that gets printed out, it often depends on the complete whole execution of things that happen. And in fact, a lot of the work on slicing literature has shown that slices can be up to a third of a trace for those particular kinds of software architectures where output depends on almost everything that happened in an application. So that, I think, is where the bigger problem is in debugging those kinds of applications. That's where things like assertions and unit testing come in, because if you have those in place, they give you hooks into starting into that questions about that output in intermediate points in the application. So they give a nice place to start that. So just let me summarize a bit here, and then we can get to questions. Current tools require people to guess, and this costs time and accuracy of knowledge and a lot of money, honestly. And the whyline tries to limit all of this guesswork by basically letting people work backwards from output that they saw or expected to see. And as a result, they've shown that it saves people time and improves a lot of their success. I have a lot of interest in extending this to lots of different contexts, including a release to the public in about a month, and looking into educational opportunities to see how well it would be good at teaching debugging skills, because it sort of embodies this systematic notion of debugging. Looking at the whyline for teams, how well does it work as a collaborative tool? What kinds of annotations would people put on it if they were working as a team? And then exploring all of the challenges of getting the whyline to work for multiple languages, where you have a program written in lots of languages, or a program that executes across lots of different machines, especially networked applications or web applications, where not only are there many languages, but there are many machines that are interacting. In terms of things outside of the whyline work, I have a lot of interest in software engineering. One of the challenges of debugging that I found from my study here a couple summers ago is that even if you find the cause of some problem, you often have to know what other constraints there are on that code that you want to change. Was this written for performance? Was it a security audit that resulted in this change? And how do all of those get woven together? So I'd like to understand that problem in a little bit more depth. I have a lot of interest in programming language design as well, especially from the perspective of what if you designed a language purely for debugging or purely for collaboration or really targeting a language to a particular purpose? What does it end up looking like, and how does that manifest itself in the use of the language itself? So I'd like to thank my thesis committee, all the past and present HCI students that I've worked with, and I'd be happy to take any questions. Yes.
So I think we can all agree that causality while debugging by doing data flow analysis and control flow analysis is something that we all want. I'm curious if you have comments about the difference between providing a tool that just supported that, like let's say if your tool didn't propose any questions, but it still allowed you to, somehow point to the color of your component and say, show me all the analysis and causality for this, versus actually posing and generating questions automatically.
The questions are basically a front end for that same kind of analysis. So really it's just a question of how do you want to present these analyses? How do you want to allow people to invoke these analyses? And what it comes down to there is how do people frame those questions in their own mind, and how much mapping do they have to do from what they see on the screen to that query? So one of the things I found in my studies, for example, is that in that mapping process to their natural language question they might phrase in their head, to the questions that I support, there's always some distance, right? I'm not going to come up with the exact question that they want to know about. It's more about coming up with the closest match to those questions. And I can reflect on those explicit kinds of queries outside of the context of a question, because all of those follow-up questions are exactly what you're talking about. It's pure data flow kinds of analysis, control flow kinds of analysis. When people understand those concepts, they know what questions they want to ask. But most of the developers that I had in my study didn't understand these notions of control dependency and data dependency. They understood what a question was, though, right? So it's partially a training problem. Once they understand that concept, I think they'll be able to use the tool in a much more powerful way. Until then, there has to be a nicer way to present those kinds of queries. Other questions?
So I'm wondering if you've thought a little bit about how the whyline might fit into a professional context like Microsoft. So here there's typically a division of responsibilities. You'll have a tester who's responsible for bug repro, and will produce a set of repro steps in a bug description, and then a dev will take it from there. But it seems like the whyline kind of sits on that edge between the two responsibilities, right? It's a lot about visible execution behavior, but it's also a little bit about internal working. So if we were living in the whyline era, how does that split of responsibilities look, or do we not split the responsibilities?
Sure. Yeah. Well, so I do have a vision of how this would all work in the future. I mean, it's sort of like a pipeline. You reproduce the failure, whether it's in the field, and there's some great techniques for doing that in a low overhead kind of way, or with a tester, and you generate this artifact. You generate this recording essentially, and what that becomes is sort of the central repository for all of that conversation, kind of replacing a bug report in a sense, because that's where it all happens right now. That's where the testers and developers collaborate on solving these problems. So if you can take those conversations, take those debates, and put them all in the context of one of these recordings, all of a sudden, all of the references that people make to things happening in the source code, rather than saying, the component that does the X, Y, and Z, they can just say this, right? And talk about that in context. I could imagine people building little tiny narratives about the causes of some problem and saying, well, if you look at this thing here, it's coming from this place, and this component over here really needs to stop doing this because it's causing this problem. And having all of those conversations in the context of not only the code, but the design and also the corresponding output that people ended up seeing, and just kind of filling the whole thing with annotations so that people could use this as a way of capturing that conversation. So I think it would be a great opportunity to streamline a lot of those conversations that happen in bug reports between these different roles.
Would there be a standard way for, say, a tester to describe the output incorrectness, like this stroke should be red, and have that be consumed by the tool, and then you can skip the questions and go directly to the
Yeah, well, the interesting thing about these questions is the way that I conceived of them was as some sort of implicit specification like that. When you say, why didn't this thing happen, you're saying it should have, right? When you're saying, why is this X, you're saying that this shouldn't be. And so if you take all of those things and treat them that way, you could imagine really directly mapping them down to the analyses that you'd want to do. Another way of thinking about it is, say you have a bunch of unit tests. Those are all implicit specifications of what you expect to happen or not happen. You don't even need a person in that situation. You can just sort of automatically generate these answers based on these failing tests and sort of have some machine in the background generating all of these answers so that whenever somebody wants to go and pursue that investigation, the data is all there. All of the loading, all of the transcription, all of the recording has been done. It's just a matter of going and investigating it.
So do you have an underlying query language?
Yes.
You do, okay.
Yes, the questions are really a front end onto that.
So in a number of the bug reports, they seem to have the commonality that a large part of the challenge with existing debuggers was finding that event handler or that other piece of code that solved it. And you really didn't even necessarily need to navigate to a particular instance. Would have been a great help to just get there. Was that true across, or was this just an anomaly of the bug reports you presented?
Finding it is always hard, especially with a lot of imperative languages, because control gets distributed across lots of different files. An interesting thing about functional languages is that that doesn't happen as often, and so you don't end up with this locality problem. If I understand your question, basically, I think that this is a language issue more than anything else. The way that we design our applications with languages affects the kinds of bugs that we end up with, and it affects what's challenging about diagnosing those bugs. So I think that I saw these particular failures, I saw these particular kinds of bug reports because of the languages that were used to implement these applications more than anything else.
But did you have bugs where it was really trivial to find, like, where to start, but it was difficult to find the bug, or were all the bugs of this sort where it was like, once you found the handler, you were 50% of the way there?
Task 2 that I mentioned for my study had both of those challenges. Finding the place was difficult. This helped with that. Finding out why that place was doing the wrong thing was also difficult. And so in this case, this list that was being generated, it was actually a set. And there was a set equality definition that basically was based on the simple, unqualified names of the classes. So people had to understand where that comparator was doing its work, what it was comparing, and where those names were coming from as well. The nice thing about the whyline is that even though it wasn't saying, this is doing the wrong comparison, it gave all of the data that they needed to determine that, right? Because they could immediately see, oh, it's comparing my class and my class. With a regular kind of debugger, even if you find that place, you have to sort of step there and get to that place and see that data before you can get there. It was immediately apparent once they found the wrong place in that task.
So you recorded each individual add to the set?
Yes, this is a full execution history. So
it's everything that happens. It's not just the things that happen that are affecting output.
Right. It's all of the output and all of the other intermediate state. Andy?
6 out of 10 people who didn't succeed in task 2 with the whyline, why did they fail?
This is an interesting line to draw because it's not all that clear how you define success. Many of those people that failed by my definition found the right place in the code, didn't end up finding why the list or the set was being computed improperly, right? So they were in the right files, they found the right places, they were in close proximity to the actual failure, didn't quite understand exactly how all of the data was related to each other. And basically the definition of success was, in their change recommendation, if their particular solution closely matched enough the solution that was implemented in the open source project. So it was a very high bar to get to the actual solution. A lot of them came up with more superficial changes to the source code that I didn't count as successful, even though they would have sort of solved the symptoms of the problem, but not really the root causes.
So let me just do it on. Once they got close, did they continue using the whyline to ask irrelevant questions, or did they just stop using the whyline and then try to comprehend the program themselves?
They used the control and data dependency arrows that I presented to follow the data that was there. So they still continued to use it. And the other thing I should point out about task 2 especially, most of them that did find the problem only found it maybe after 15 minutes and spent a lot of time understanding the other source code and the other context. I think if they would have had an hour, a fair number of them probably would have come up with the right solutions to the thing, because they were all following the same basic path but at different speeds. So I think this could have just been sort of a ceiling effect where had they been given more time, they would have found it. The control group participants just had no hope, though, right? They had this locality problem. There was a massive amount of code, and they just weren't able to find it. So, yes.
You're instrumenting that on a line level basis, right? Because in order to track causality for something is set.
I'm instrumenting on an instruction level, in fact, for each bytecode instruction. So not even just source code lines.
There's an example where they're moving the mouse around during a stroke. I mean, you actually use that application while you're in instrumentation.
Yes, it's still usable. And in fact, there are some easy engineering ways to get around the overhead of doing that. Just by instrumenting the virtual machine instead of the source code itself, you can reduce that overhead by a great deal. But even then, it was still usable from a user interface perspective. And the sizes of the trace, especially those strokes that were drawn in that painting application, the canvas repaints itself and does the exact same work multiple times, but it all compresses very well because it's the exact same pattern of output over and over again. Let's go in.
Go ahead, yeah.
Is tangent thought on performance debugging? What would you do?
It's sort of out of the scope of the kinds of questions. And most of the questions that people have about performance are, why was this slow at this time? And so it's all about specifying this and this time. So this is a great way of getting at that time specification about saying when something was slow. And it's also a great way of pointing to what you thought was slow. So I think there's some thinking that needs to be done to figure out what kinds of analyses would actually answer that question. But it might be an opportunity to take a new look at performance profilers and think about ways of capturing the right data for those questions, rather than having people guess what was slow and then go gather data about it in the same way that we do with debugging.
All right, so let's thank Andy one more time.